Welcome to another deep dive. I think we can jump right into it. You and I both have this fascination with philosophy, right?
Mhm.
And the pursuit of trying to grasp these really big, complex ideas. So we're going to take a deep dive today into a topic that sits right at this fascinating intersection of logic and philosophy. It's called the combination of logics.
It is interesting because in philosophy we often talk about like synthesizing ideas or reconciling different viewpoints, and it's almost like what we're exploring here is something even more foundational. It's the formal methods that logicians use to connect and analyze different systems of reasoning, like right down to the very architecture of how we structure thoughts.
Yeah, that's a great point. And so to navigate this intricate world, I think the STEM Encyclopedia of Philosophy entry on combining logics is a really great starting point. It gives us a solid foundation for this deep dive.
For sure. And I think what we want to do today is really distill the core motivations and the methods and most importantly the implications of combining logics. And this is going to be particularly relevant to you, given your interest in philosophy. We want to go beyond just defining what these combined logics are, but really get into the why. Why should a philosopher care about these things?
Yeah. Okay, so let's unpack this a little bit. One of the very first questions that comes up in the source, and it's such a philosophical one, is why are there so many logics, right? Why isn't there just one? Why do we have this multitude of systems? It's almost like logicians can't stop themselves from coming up with new ways to think.
Yeah, well, the field of combined logics, it really offers an interesting perspective on that. It suggests that maybe these logics aren't necessarily isolated or in competition, but they're compatible tools. Maybe each of them is suited for analyzing different kinds of concepts or different kinds of arguments.
Mhm. Right. And then we get to this notion of mixed logic systems, which the source highlights as a really intriguing example. It uses arythetic logic, which is the logic of questions, as this sort of case study, right?
Hmm.
And points out that if you really want to analyze questions in a rigorous way, you can't really avoid bringing in things like epistemic logic, the logic of knowledge, and deontic logic, the logic of obligation and permission.
Absolutely. And it just shows how a lot of real-world philosophical problems, they just don't fit neatly into one single logic, right? You need to sort of bring together multiple systems of reasoning to get a, a better picture.
Right. And speaking of these sort of classic philosophical problems, I think the is ought problem,
Yeah.
which the source also discusses, is a really important one. And of course, this goes back to Hume's observation about moving from descriptive statements about what is
Sure.
to prescriptive statements about what ought to be, right?
Right. And this has been a point of debate in ethics that I mean for centuries now. And the consensus stemming from Hume is that you can't just derive an ought from using just simple logical inference.
Right, but then this is where this idea of combined logic starts to get really fascinating, right? Because as the source mentions, some thinkers have proposed these things called bridge principles, and these are like explicit connections between the I's and the ought, right?
Yeah.
And you have something like P implies it ought to be that P. So this looks like a kind of direct connection between the two domains, but
Right.
but of course it's immediately philosophically suspect, right?
Yeah. I think another example is the idea that ought implies can, right? So if something ought to be the case, then it must be possible for it to be the case,
Hmm.
which is formalized as be. So the obligation operator implies possibly p, which is the possibility operator. And I think the source really does a good job of making it clear that these bridge principles, they don't just solve the is ought problem,
Right.
but what they do is they provide this really interesting formal framework. Combining deontic logic with alethic logic, it allows us to really analyze the independence of the I's and the ought domains, right? You can really see how they operate under different rules.
So by actually combining the logics, you can see at this structural level why you can't just make this simple jump, right?
Exactly.
Yeah.
You're essentially doing a formal analysis using composition or decomposition of these logics.
Hmm.
And that highlights the difference in the logical behavior, right?
Yeah.
So it's a way of using the precision of logic to kind of illuminate this really deep philosophical problem.
Right. And then the source brings in Pryor's paradox, which I think is a really interesting um, sort of twist in this whole discussion, right?
Yeah.
Because it deals with these sentences that mix normative and non-normative elements.
This is where it gets really interesting for any philosopher who's thinking about logic and ethics, right? So Pryor shows that if you have these sentences that blend descriptive and normative content and you apply, just standard classical propositional logic to them, you can end up with these inferences that seem really problematic, right? So, one example is if you have the sentence, "The sky is blue."
Right.
Therefore, either the sky is blue or everyone ought to be kind.
Yeah.
And that's a perfectly valid inference in classical logic.
Right. Yeah. It's logically sound, but philosophically, it's very unsettling, right? Because it looks like you're getting an ought from an is. And Pryor sort of took this even further, right? He said, well, this kind of thing happens no matter where you try to draw a clear distinction between these two types of sentences, right?
Right.
And he even argued that maybe Hume was wrong. That maybe you can derive ought from is based on this logical issue.
It's definitely a provocative thought, but I think Pryor himself acknowledged that a lot of these derived ought statements, they often end up being ethically irrelevant or trivially true, right?
Right.
And the real challenge then becomes, how do you actually define this idea of irrelevance in a formal way?
Right. Right. And that brings us to Schertz and his generalized Hume's thesis.
Yeah.
Which is a way of trying to address this issue, right?
Yeah.
And his approach looks at the fusion of alephic and deontic logic, which actually segues nicely into the next sort of major part of our discussion.
Yeah, I mean, this is where things really start to come together.
Mm-hmm. Right.
So what Schertz shows is that in this combined alephic deontic first order logic, you can only derive a mixed sentence, one that has both is and ought components, from a purely descriptive sentence if that mixed sentence is irrelevant to the deontic operator, to the ought.
Right.
And he makes a really strong claim that this is the case if and only if the logic itself can be axiomatized without those bridge principles that we were just talking about.
Right. So it's like these Briggs principles really they're at the heart of the whole issue, right?
Yeah.
And the way that we combine these logics, it either allows for them or prohibits them.
Formal architecture of the combined logic dictates, can you make these connections or can you not?
Yeah. Yeah. And then the source just very briefly touches on a couple of other areas where this kind of thinking, this idea of combining logics and looking at these bridge principles is relevant. It talks about things like the logic of physical and alethic modality. So, the relationship between what's logically necessary versus what's physically necessary.
Yeah. This principle that if P is logically necessary, then it must also be physically necessary is a good example of a bridge principle in that area. And again, it points to the different sort of strengths and scopes of these different notions of necessity.
Right. Right. And then the source moves on to this broader sort of underlying motivation for studying combined logics. And it mentions this idea of pluralism, logical pluralism.
Yeah.
Which has become quite influential in logic in recent years.
Right.
So I idea that there isn't necessarily just one, correct logic for everything. Yeah. Right. So if you have this plurality of logics, then it becomes a really interesting question. Okay, well, how do these different systems relate to each other? And that's where, combining them becomes a way to sort of try to understand those connections and overlaps.
Yeah. And I think Van Bentham makes the point that you can even have, new logical phenomena that emerge from combining logics, right?
Yeah.
Insights that you wouldn't get if you just studied those logics in isolation.
Right.
And he also, I think he pushes back against this idea of separating out all the different areas of logic, like keeping modal logic separate from temporal logic.
Mm-hmm.
And his point is that, a lot of philosophical problems involve multiple concepts at the same time.
Right.
You have necessity and time and knowledge.
Mm-hmm.
And so he thinks that combining the logical frameworks that govern each of those concepts individually, might actually be a more powerful and a more nuanced way to approach these traditional philosophical problems.
Yeah. Yeah. That makes sense. So we've sort of looked at the why, right? Like why are people interested in doing this? But then the next question is, okay, well, how do you actually combine logics? And the source introduces this distinction between splitting and splicing.
Right. I think that's a really helpful way to categorize the different approaches.
Yeah.
So splitting or decomposition is essentially taking a complex logic and trying to break it down into smaller, more manageable parts.
Right.
And then splicing or synthesis is about taking a bunch of logics and putting them together to create a new logic.
Right. Okay. So under this splicing umbrella, you have things like fusion, for example,
Right.
which is one of the kind of early general techniques, right?
Right. So fusion is particularly useful for modal logics.
Mm.
So imagine you have, two different logics of necessity, right?
Right.
So you might have box 1p, box 2p,
Yeah.
and one of them could represent, say, metaphysical necessity. The other one could represent physical necessity.
Right.
And what fusion does is it creates a new logic that incorporates both of those necessity operators. So you have this new logic that has both of these notions of necessity built in, but they're able to function independently of each other.
Yeah, these two different necessity operators that can interact.
Yeah. So each operator kind of keeps its own semantic rules.
Mm-hmm.
And these rules are usually defined in terms of accessibility relations in Kripke models. And this allows you to create formulas that combine these different modalities. So you could have, something like box 1, box 2p implies p.
Right.
So you're nesting these modalities from the two different logics, and axiomatically what we're doing is you're basically just combining the axioms and inference rules of the original two logics.
Right.
And they usually share the same
Yeah.
logical connectives,
Right.
like and or not implies.
Mhm.
So it's a pretty straightforward way of bringing these two systems together.
Right. And the source mentions Schurz's logic and Fitting's work
Yeah.
as kind of examples of this approach. And it mentions that there's actually been a lot of work on figuring out which properties of the original logics are preserved under fusion.
Exactly.
Right. So, like things like completeness or decidability.
Yeah. Yeah. And that really gets at, both the robustness and the limitations of fusion as a method.
Right. Okay. Then we get to products of logics,
Right.
which is another kind of splicing technique. So how does that differ from fusion?
So products, which were really introduced by Segerberg and Shapeman,
Okay.
they're particularly useful when you're trying to represent information about multiple dimensions, like time and space. So the way that products work is you don't just have the two logics sort of sharing the same set of possible worlds.
Mhm.
You create a new set of worlds by taking the Cartesian product of the sets of worlds from the original Kripke models.
Mhm.
So a world in the combined logic is actually an ordered pair of worlds,
Okay.
one from each of the original models.
So you're kind of multiplying the possible worlds.
Exactly. And the accessibility relations for the two modalities are defined in terms of this product structure. And what's really interesting about products is that new interaction principles, those bridge principles that we were talking about before,
Right.
they become valid in product logics.
Yeah.
So you might have, like commutativity of possibilities. So diamond 1, diamond 2p implies diamond 2, diamond 1p.
Okay.
Or Church-Rosser-like properties.
Right. So these kinds of interactions between the modalities, they're not something that you have to add in explicitly. They kind of come out naturally.
Exactly. So unlike fusion,
Yeah.
where you have the modalities remaining independent unless you explicitly put in axioms to connect them,
Mm-hmm.
products actually generate these connections just by virtue of the way that they're defined.
Right. And so that means that you can't just take the axiom systems of the original logics and just put them together.
Right.
Right.
Yeah, well, because you have these new interactions, you have to explicitly add axioms that capture these new bridge principles
Yeah.
to get a complete system.
Right. Okay.
And it turns out that axiomatizing product logics can be really tricky. And there's even this thing called the finite crash phenomenon,
Okay.
where the product of two finitely axiomatizable logics,
Mhm.
it turns out to be non-finitely axiomatizable.
Okay. That's really interesting.
Oh,
Right. Then we have fibering, which is often called fibering by functions.
right.
And this sounds like a more complex approach, right?
Yeah.
Yeah.
So Gabby's approach to fibering uses these Kripke models that have designated worlds, these actual worlds.
Okay.
And then you have these transfer mappings between the sets of possible worlds of the two logics that you're combining.
Right.
So when you're evaluating a formula from one logic in a model of the other logic,
Right.
you use these transfer mappings to shift the evaluation to a corresponding world in a model of the second logic.
Okay. So it's like the truth of a statement in one logic is kind of dependent on the truth of some related statement in the other logic.
Right. So you have these transfer functions that kind of act as intermediaries.
Okay. Right.
And the satisfaction conditions for modal formulas in the fibered semantics are defined in terms of these mappings.
Right.
So you're kind of jumping between the models of the different logics and like products of logics. Often when you axiomatize a logic obtained by fibering,
Yeah.
you need to add new bridge principles
Right.
to guarantee completeness.
Then we have this idea of categorical or algebraic fibering, which sounds even more abstract and more general.
Yeah, this is really, really interesting stuff.
Yeah.
So Nadas and his colleagues they developed this approach
Mhm.
using category theory. Mm-hmm.
To kind of overcome some of the limitations of the earlier methods and to provide a more unified framework. So the basic idea here is that you treat logics as objects in a category,
Right.
right? And then the process of combining them is defined in terms of this universal construction.
Mm-hmm.
It's analogous to the coproduct in category theory.
Yeah.
It's like you have these different building blocks, these different logics, and categorical fibering gives you these really general rules for putting them together in a well-defined way, even if the logics have different shapes.
Right.
Right.
Yeah.
Like different ways of connecting.
Okay, so if you have two logics and they don't share any logical connectives, then the combined logic is just their sum.
Yeah, exactly. So that's called unconstrained fibering.
Mm-hmm.
But if the logics do share some connectives, like the standard classical connecting.
Then you do this constrained fiber
Mm-hmm.
where you use these things called coequalizers in the category to make sure that you're identifying those shared elements properly.
Right. Okay.
And what's really neat about this is that the fusion of modal logics that we talked about before,
Yeah.
that actually turns out to be a specific instance of this more general categorical fibering approach.
There's it's like a subcase.
Exactly.
Like that.
Exactly. And the nice thing about this approach is that it's not limited to modal logics, right?
Right.
It can be applied to a lot of different kinds of logical systems, no matter how they're presented. So you could have, Hilbert style axiomatic systems, you could have, sequent calculi,
Mhm.
you could have, a lot of different formalisms.
Right. And
This approach
this approach works for all of them.
Okay. So that's really powerful then, right? It is. And because it's a universal construction, it has, nice, well-defined formal properties.
Mhm.
But it can be really tricky to figure out exactly what the semantics of the resulting logic are.
Right.
Just based on the semantics of the component logics. And so researchers are still trying to figure out, how to do that. And they're using things like non-deterministic matrix semantics as potential solutions.
Okay. So those are the main sort of splicing methods.
Yeah.
Then we have splitting, which is the opposite.
Right.
And the text focuses on this approach called possible translation semantics, or PTS.
Right. So this is Carnielli's approach, and it's kind of the opposite, like you said, of splicing. So instead of building a logic from simpler logics, you're trying to decompose a logic into simpler logics.
Right.
And the way that you do that is by defining a set of of translations
Hmm.
between these logics. So the idea is that a formula is derivable in the original logic, the more complex logic,
Hmm.
if and only if its translations are derivable in all of the simpler logics.
Right. So it's like taking a complex object and trying to see it from different angles, right? You
Exactly.
have you have these
Yeah.
different lenses.
And this is really useful for analyzing logics that maybe don't have straightforward semantic interpretations.
Hmm.
Like, some of the paraconsistent logics,
Right.
the logics that can handle contradictions without everything just exploding.
Right.
And so what you do is you translate these logics into systems that we understand better.
Hmm.
Like many valued logics with finite matrices. And that can give you a better understanding of the properties of these original logics.
Right.
And you can even use it to prove things like decidability.
Right. So it's a way of kind of making sense of these more opaque logical
Yeah,
systems.
exactly.
Right. Okay. And then the source mentions just briefly a couple of other techniques like temporalization, parameterization, and institutions,
Yeah,
which seem to be more geared towards specific applications.
right.
Right.
So temporalization and parameterization, they involve replacing the atomic components of one logic with formulas from another logic.
Okay.
Right? And institutions are a very abstract model theoretic framework
Hmm.
for dealing with specifications that use multiple logics.
Right.
And this is particularly useful in software engineering.
Hmm. Okay. And then finally, there's this section on new perspectives,
Right.
which introduces things like graph theoretic fibering and importing logics.
Right. And these are really just kind of, ongoing developments in the field.
Hmm.
And they're really aimed at overcoming some of the limitations of the earlier methods and broadening the scope of combined logics.
Right.
So these new approaches allow us to handle more expressive logics, like some structural logics,
Hmm.
and to combine logics at a finer grain level.
Hmm.
Even at the level of individual models.
Right. Right. Okay. So that's quite a comprehensive overview of the methods, right?
Yeah, it's a lot to take in,
Yeah.
but it's really, really fascinating stuff.
Yeah. Now the last major section of the source deals with these sort of perplexities, right?
Right,
These
yeah.
problems that can arise when you try to combine logics.
Right.
And it talks about this issue of lack or excessive interaction.
Yeah, and this is where I think the philosophical implications really start to come out.
Yeah.
So just because we can combine logics formally, it doesn't mean that we're always going to get, a coherent or a philosophically insightful system.
Right. Right.
And so one big problem is this thing called the collapsing problem.
Right.
And the source uses the example of combining, classical and intuitionistic propositional logic.
Mhm.
And what can happen is that if you just naively combine these two logics at the semantic level,
Mhm.
you can end up with a system that collapses back down to just classical logic. So you lose the distinctive features of intuitionistic logic.
So even though you're combining them, you're not really getting something new. You're just
Yeah.
getting classical logic back.
Exactly.
Right.
Yeah.
And that's not what you want.
No, not at all. And the deduction meta theorem plays a big role in this collapse. But the source also points out that this collapse might not happen if you combine the logics at the level of Hilbert calculi.
Right.
So again, this shows how the specific method that you use to combine the logics can really make a big difference.
Right. And then there's this interesting observation by Bezial about how you can get distributivity when you combine the rules for classical conjunction and disjunction.
Right.
And it's like the logic becomes too strong in a way, right?
Yeah. Yeah.
Because it derives principles that weren't there in the original logics.
Exactly.
And so this is kind of an example of excess interaction.
Right. Yeah.
Right. But then on the other hand, you can also have a situation where the combined logic is too weak.
Right.
And it doesn't derive certain interaction laws that you would expect.
Yeah. Yeah, so one example of that is if you combine classical negation and disjunction,
Hmm.
and you use certain algebraic fibering techniques, you might end up with a system where the law of excluded middle,
Hmm.
which is, a really fundamental principle in classical logic,
Right.
it might not hold.
So you're losing something
Exact.
that you would normally expect to be there. Right.
Exact.
Okay. So it's really a delicate balancing act, right?
It is.
You need to have enough interaction between the logics, but not too much. Right.
Exactly. And